welcome to our ongoing celebration of 20 continuous years of human presence on the International Space Station. I'm Tara Ruttley, Associate Chief Scientist for Gravitational Research at NASA headquarters in Washington, D.C. Over the past 2 decades, NASA and its partners have successfully supported humans living in space aboard the International Space Station since the Expedition 1 crew of Commander William Shepard, Sergei Krikalev, and Yuri Gouzenko, who arrived November 2nd, 2000. So this November 2nd began the 20th year of continuous human presence living off the planet on board the station. A truly global endeavor, this unique microgravity laboratory has hosted more than 240 people from 19 countries, conducted more than 3,000 experiments from over 4,000 researchers who are from more than 100 countries themselves. And the station has hosted a variety of international and commercial spacecraft. Conducting science on the station provides an unparalleled way to address the challenges of moving humanity toward the moon and Mars, which is what we want to do, while increasing knowledge of engineering, physical sciences, biology, our own planet, and the universe. In the 20 years that humans have lived on the station, we built our understanding of how we can safely live in microgravity and work there and stay there longer and longer. And we've made some pretty groundbreaking discoveries. So today I get the fun opportunity to chat with my friends and colleagues who I've worked with for many years in the space station program down at the Johnson Space Center about those discoveries and their experiences with the science and technology activities happening on the station over the past 20 years. Marybeth, Kirt, and Jennifer, since I joined NASA in 2001, there's always been humans in space. It's for my entire career. Many of those watching now are 20 years and younger, and they can also say they've always been a part of the time when humans have been living in space. Would you please introduce yourselves, tell us what you do for the space station program, and share with us where you were or what you were doing November 2nd, 2000. Marybeth?
Hi, Tara. Sure, I'd be happy to. So my name is Marybeth Edeen. I manage the research office, and our job is to get all of that research that we're going to talk about up into the space station so that it can be executed by the crews. I've been in NASA for over 30 years, and on November 2nd, 2000, I was actually working on the life support systems. I was a life support system manager, and I would have been on console in the mission evaluation room, in the back room, supporting the flight team, watching for the crew to enter the space station and make sure the little bitty life support systems we had at that time, which were really kind of just fans and maybe some airflow systems and smoke detectors, were working properly when the crew got on board.
Great. Thanks, Marybeth. And how about you, Kirt?
Thanks, Tara. Hi, I'm Kirt Costello. I'm the ISS Chief Scientist and also the Deputy Manager for the Research Office. And what we do is make sure that all of our sponsors have access to the ISS to conduct research and make sure that we follow NASA's priorities in laying out how that research gets done. So back in 2000, I had just started with NASA. So, in fact, that was in September. So in November, I was probably still learning NASA acronyms at the time, although I'd been doing some work before then with some flight software. I was hired on as a training instructor for the electrical power and thermal control systems. And at that time, I remember we were desperately trying to get ready for the crew training for the arrival of the U.S. lab. So while the node was already there, and I was glad that they had access to that module and the U.S. software to monitor that module, we were working on the next big module, the U.S. lab.
Thanks, Kirt. You know, one thing I remember about being a new employee, too, was learning all the acronyms. NASA has like a link to like a list of all the NASA acronyms and their definitions for all the newbies like us, and I still use it to this day. All right, Jennifer, tell us about yourself.
I'm Jennifer Buchli. I am the ISS Deputy Chief Scientist. So similar to what Kirt mentioned, we support science for the ISS program. And specifically, I spend a lot of my time managing the research priorities for ISS, making sure that we are utilizing the space station efficiently and accomplishing science for all of our sponsors. In November 2nd of 2000, I was living in Austin, Texas, attending the University of Texas, Austin.
Oh boy, yeah. Some newbies and some of us a little bit more veteran, but that's good. That's what makes this a great panel. And I'm thrilled I got to work with you guys for Marybeth. I think my whole career is somewhere on and off, and then Kirt and Jennifer over the last 10 years. So this will be a fun hour. Okay, so I've got some questions for you guys. This is what everyone wants to know, right? And the first one is for Kirt. We constantly say the ISS is an orbiting laboratory, and the point is to do science in space. But why? Why bother doing science in space to begin with?
Thanks, Tara. That's a good question. It's really a question, though, for all scientists. And why do we go out into the field to do science? In this case, it's the environment of low Earth orbit. Low Earth orbit and space give us several unique capabilities that we can't get to here on Earth. First off, there's the exposure to microgravity. When you have a microgravity environment, this eliminates buoyancy-driven convection, and it eliminates sedimentation. So those two factors no longer occur in physical processes. When you don't have that single force of gravity always pulling down on you, you're able to look at systems in a way that is a little bit less complex, and also where those forces that are masked by the force of gravity aren't able to be observed. So microgravity gives us a unique opportunity to observe those forces. The second is purely the access to the space environment. In low Earth orbit, we've got two things: the exposure to space radiation and the space radiation environment, understanding how it affects materials, how it affects biology within the space station even. That's one of the goals for us to continue our exploration out into the solar system and beyond. And then finally, having access to external sites on the ISS gives us the opportunity to both look up at the heavens above and down on the surface of the Earth below. From the astronomy standpoint, we're above the atmosphere of the Earth, and that allows us to do observations that would be obscured by the atmosphere here on the Earth. From the Earth observation standpoint, we have an orbit that covers about 85% of the surface of the Earth. And we also have this special orbit that allows us to go over the same point on the surface at different times of day. So that allows scientists to look into what are called diurnal effects, or what happens at different times of the day. So you can tease out through those observations different behaviors that you really don't get through traditional means.
Yeah, I've been really fortunate to work in space station my whole life, or my whole career. I feel like it's my whole life, my whole career. And I've been in love with space my whole life. But the really cool thing is, if you're a scientist, those discoveries that you can make that no one has ever made before, that's what the space station offers. Like you said, with gravity gone, anything's possible that you may not have even seen before. So it's an exciting time to have a research platform that's lasted so long and has given us so much. My next question is for all three of you. Each of you can answer. Many people may know that there are astronauts doing something up there on the space station, but they may not know about the benefits that have been rolling in for the past 20 years. A lot has been going on. The benefits can apply to those of us here on Earth, and also in advancing human exploration of space. We can go further. Can you each share an example of a benefit that has come from the space station research and technology testing? And I'll start with you, Marybeth.
Sure, I'd be happy to. So I'm going to build a little bit on what Kirt was talking about those Earth observing instruments. One of the real benefits that come from space station is that precessing orbit that he mentioned, of how we cover, 85% of the globe and 90% of the populated landmass. And the beauty of station's orbit is that it crosses the orbit of a bunch of other instruments that are in the sky. Lots of instruments that point at a single point on the globe. And so by crossing our orbit across those with similar instruments, we can cross-calibrate those instruments and our instruments, and then we can really expand those data sets because we can cross European instrument orbit, we can cross a United States instrument orbit, we can cross a Japanese instrument orbit, or Russian, or even other countries, and then we can take all of those data sets and we can say, okay, well, at this point, all of these things, this is how these instruments are all related to each other. And then we've made the value of those individual instrument data sets significantly greater because we've now been able to compare across the whole globe. As Kirt also mentioned, the diurnal cycle, the day-night cycle. Most of these instruments are on a stationary orbit and they see only, daytime or only nighttime, depending on where they are and what they're looking at. And so by having instruments on ISS that give you day and night data, then as you then cross these other instrument orbits and things, you can also then start to tease out even more information about what you've been able, what the instruments are telling you over time. And the other thing that we've been able to do with these instruments is some of the instruments are getting very old in orbit. And there was a number of years ago, an instrument that had expected life of, I don't remember if it was like 10 years, and it had been up there 15, and they were very concerned about it failing. But it was the quote gold standard for calibration of this type of instrument. And so they put an instrument on ISS and they were able to transfer that calibration standard to the ISS instrument until the next higher quality instrument gets into orbit in its own, unique orbit. So it's been a multiplier of the value of many, many other instruments, Earth observing instruments specifically, that otherwise wouldn't have been able to be done.
Right, and observing the Earth for disaster response or looking at crops or things like that on our own planet. Yeah, that's a huge
CO2 levels, yep. Moisture, water vapor, all kinds of things. Lightning imaging, all kinds of climate and weather-related activities.
Yeah, excellent. Our own planet. Thank you, Marybeth. Jennifer, how about you?
Yeah, so one area that's really active in ISS research is biotech and biological, including pharmaceutical research. So something that we know from ISS is that structures more readily form 3D structures in microgravity. So things like cells adhere together to form 3D structures. Tissue engineering is a big area of research. And then another one for the pharmaceutical industry in particular is protein crystal growth. So we have done over 500 protein crystal growth, or PCG as we say, experiments on ISS. So what this is these are proteins that are associated with the disease state here on the ground. And they can be really hard to mimic or form and then study here on the ground. They're very fragile. And so when you take them out of the body and you try to create them in a lab, gravity tends to pull down and make these structures really hard to create. So using ISS as a platform, we can help these complex structures form in a way that they are larger and have a higher yield than they would here on the ground. So this really aids in drug design. We've studied this in multiple disease states, Alzheimer's being one. Another one that has been highly successful has been Duchenne's muscular dystrophy. So this is a disease state with progressive muscle wasting. So one of the experiments we did on ISS, we were able to actually grow these crystals on the space station, return them, and then a pharmaceutical company designed a drug based on those crystals, which is now in use here on Earth and humans.
That's right. I remember that one. That was our JAXA colleagues, right?
That's right.
Yeah, that was the first big one that we were really, really excited about, the hidden water molecule. Yeah, that was good. Thank you, Jennifer. How about you, Kirt?
Yeah, for those who were wondering what I said, the lack of buoyancy-driven convection, let's paint a little bit of a picture. Imagine you're now sitting around a campfire. That campfire flame is dancing and blazing away. But what you're seeing is the turbulence caused by that convective airflow and the hot gases leaving the flame itself. Imagine if your job is, as a scientist, to help devise a more fuel-efficient car. You need to know about combustion. You need to understand how things burn. And now imagine that being your job. Somebody says, okay, well, your job is to create a model of that fire right there. One math model to explain all the dynamics in that fire is going to be really hard to develop. And so people got the idea that studying combustion in space is going to be particularly beneficial. In microgravity, you don't have that buoyancy-driven convection, so you don't have a lot of the turbulence involved in the combustion effects. And so people started observing the burning of flames in space to better understand the mathematical models behind combustion. One of our early experiments in this area, called FLEX, stumbled upon the fact that they were seeing evidence of burning, combustion, at much lower temperatures than a conventional fire burns at. What they had stumbled onto was an effect called cool flames. This is a very unstable effect on the Earth. You might experience it when you've got an old car engine that knocks or sputters when you try and turn it off. But in space, that becomes a more stable thing. So you can actually study it over time. And we've done subsequent experiments, both in the FLEX series, the FLEX 2, and an investigation called the Cool Flames investigation, that have generated a ton of data as to how this cool flame actually burns. And what does that mean? That means we're getting data back that could one day help us understand how to design more fuel-efficient engines and burn at lower temperatures more consistently. So this is a good thing for the environment. It's a good thing for industry. Hopefully it will develop into these great experiments. But it was all enabled by the fact that you were able to just do this without gravity causing all this turbulent backflow.
Thanks, Kirt. I remember when that came out too. I remember hearing about the unexpected finding of a cool flame while they were burning liquid droplets in the combustion chamber, and then everyone was talking about it and sharing the knowledge and trying to figure out what this was they were looking at. And when they figured it out, it like you said, it led to a series of whole new investigations, a whole new path of discoveries that have all these applications on Earth and in space. So that was a good one, and I'll never look at my campfire the same when I'm burning my s'mores. I appreciate that. I'll be thinking of station combustion forever and sharing that with the children that I'm making s'mores for. All right, so let's move on to the next question. Let's go to Kirt. Back to Kirt. Not every astronaut is a career scientist. Some are medical doctors, engineers, and pilots. So how are the astronauts able to do all this science on the station if it's not their background?
That's a good question. You're right. Every astronaut doesn't come to us with a hard science degree. And even though more of them today are coming with that science background, every astronaut that comes to us, I would say, comes to us as an explorer. They join NASA with the vision that they're going to help us explore the universe. And what really drives explorers, they're curious about the world around them. They're curious about the world, and they turn that curiosity into an action that leads them in discovery. If you think about it, scientists aren't really that different. They use their curiosity to pose questions about the universe, and then they devise experiments that help them test those hypotheses. It doesn't take a lot of effort to really turn an explorer into a scientist. NASA also has a great system of support for our astronaut scientists, from our payload developers and our payload operations specialists, who really help configure the operations on board so it's easy for our astronauts to participate in the science. The other thing about our crew members, they're great observers. They're right there in the action, and they're the eyes and ears that our scientists need to understand when something isn't quite going as planned. They have the benefit of being able to jump in there and tell them, hey, we're seeing this really neat effect. And they've done this before in some of our experiments, and then helping the PI remap his or her plans for how to experiment on that to capture that. They also come in extremely handy when something doesn't go as expected on orbit. And we've had that happen a lot. And a lot of PIs owe their science to the ingenuity of our astronauts in helping them figure out a fix for hardware that goes awry. So it doesn't take any special background necessarily to do science on ISS. It just starts with being curious. So if you ask a question, devise an experiment, whether that's in your kitchen or your backyard, you could be the key to the next big discovery on ISS.
That's exciting. Everybody should want to be the next big key discovery to ISS. You hear that, viewers? It could be you. Yes. And everybody's an explorer at heart. You're right. I think the special thing about space station too is having people on board, like you said, the humans in the judgment calls, in the making changes on the spot, in communicating with the principal investigators on the ground is critical. And then not to mention the fact that not all of our investigations need crew time, right? We have so many of those 3,000 investigations that I mentioned earlier that are also automated from the ground, and the crew doesn't need to touch those. So you don't have anything like that off of the planet where you have human judgment in the mix of even automated instruments. So very good. Okay, the next question is for everyone, and I guess I'll start with Marybeth on it. Artemis, that's NASA's plan for returning humans to the moon sustainably over the next few years. The big one. Everyone's excited. The plan is for humans to stay longer than we did during the Apollo missions. So it's really important that we do all the work now so we can prepare to go. How does the work on ISS prepare us for that Artemis mission? Marybeth?
So I came from the life support world, and on the Apollo missions and the shuttle missions, our life support systems consisted largely of consumable items that we used up. We had lithium hydroxide to remove CO2, but once the lithium had the CO2 absorbed on it, became lithium carbonate, then you couldn't use it anymore, and you had to put in a new can of LiO, as they called it. The toilet, you vented urine overboard, and the oxygen came out of tanks after splitting the water in the fuel cell, or out of tanks for the crew to breathe in. On space station, we tried to develop life support systems that were what we referred to as regenerative, that would recycle the urine and water, wastewater into drinking water, that would remove the CO2, but not with a material that was consumed, but with a material that would absorb it and then desorb it overboard. So we did a pretty good job with space station. And we were able to close what we call close the loop. In other words, recycle a lot of the components. So our water loop is about high 80s to low 90% closed, right? So the water that we put up there, we use over and over again, and we end up losing 10 to 15% of the water as waste. And the other 85% is recycled back into drinkable water and used by the crew again. Interesting fact, the water you drink today takes about 7 days to go through your body and then through the life support systems to be the water you drink again 7 days later. So Sunday's coffee is the same as Sunday's coffee a week ago, and as Sunday's coffee a week from now will be. On the ground, that takes like tens of thousands of years, but in space station, it takes a few days. So just, for fun. But our system on station still is not closed enough to be able to go do exploration or do a permanent module on the moon or go do exploration to Mars. We have to make them better. So one of the things we're continuing to do on space station is to improve our life support systems and to try out new technologies that get us even closer to being closing our loops. So right now on space station, the urine is processed, but you end up with a very concentrated brine material, very salty. Think about taking salt water, which is pretty much what your urine is, putting it on the stove and boiling it away, and you end up with a really salty solution at the end. Right now, that's what we throw away. But if you want to recover the water out of that brine and just end up with the salt, then there's a way to recover what we call the brine recovery system, to recover the water. If we can do that, then we can close the loop into the high 90%. Then maybe you're getting close to something you can take to Mars. So the next piece going up on ISS to be tested before we do exploration is a brine recovery system. Similarly, on the air side for oxygen and CO2, providing oxygen, removing CO2, new technologies that lose less air overboard. Right now we absorb CO2 on a zeolite material, and then we expose it to vacuum, and that CO2 goes overboard. But if you think about carbon dioxide, it's got an oxygen molecule on it. And gosh, wouldn't it be good to be able to use that for oxygen again? So technologies to recover that and just have carbon as your waste material are other key things we want to test. And those are being developed and tested on station. Similarly for plant growth, if you're going to go long duration, you're going to have a permanent base on the moon, you're going to go to Mars, going to have to grow some food because you can't take all your food with you. So we're doing a lot of experiments on the space station for plant growth and how to, not just grow them once, but grow them, take them to seed, take those seeds and regrow them so that you can actually farm in space. So those are some of the key areas where we're using space station to really help us move forward and prepare for the Artemis mission and for future Mars exploration missions.
Right. That covers the force of life for humans. You've got to be able to sustain human life off of the planet, off of space station, and on to this new place, the moon, for longer and longer. We're staying there longer. Jennifer, did you have anything you'd like to add to that?
Sure. One area that we're taking a look at is really from the human health perspective too. So as Marybeth mentioned, we need to grow plants, we need to have food crops. We also need to understand how those things affect our astronauts in space. And so, in recent years, we've started extending their missions on space station. So when we first started, we were really keeping to, 6-month missions. And recently we've done several that are almost a year long. So really, how do humans adapt as they spend longer times in space and off the planet? So we've talked about under Artemis, we're going back to the moon. We know we want to stay there for longer periods of time and then eventually go on to Mars. And so we need to take a look at, physiology, how we can support our astronauts with the best countermeasures to make sure that they're successful. They're going to have these really interesting gravity transitions of going from 1G to 0G and then either to lunar or Martian gravity. So, what does their performance look like and how do we support them operationally? And then also, physiologically as well with, food or nutrition and things to help them optimize their performance and their success.
Great. Thank you, Jennifer. Kirt, did you have anything you'd like to add to that?
Sure. Switching gears just a little bit, new programs require testing lots of new materials. And space station is a great place to allow for the testing and performance of new materials in a non-critical situation. We want to know how a material holds up, what its properties are, what happens when you expose it to atomic oxygen, radiation, solar particles, X-rays, before you have to use it in a critical space application. So the ISS provides a great test bed, and it does it through one of our commercial partners, in the MISSI platform, which stands for Material Science in Space, that allows us to go out and test these coupons of test materials and get them ready for their next missions. We also consider, well, what kind of contamination do we have around space vehicles? We've got contamination that comes off the visiting vehicles, and we want to know how that's going to impact instruments. But we also have this potential question of, does humanity carry a contamination of its own biome with it on space vehicles? So we've got some investigations coming up to help us understand, hey, what kind of materials collect on the outside of the ISS over time? And are there living materials that could be a question as we go to the moon and other places in terms of the sterility of that atmosphere? So there's a lot of different ways that ISS can help support these exploration goals moving forward.
Great. Thank you, Kurt. Jennifer, I want to go back to you because you talked a little bit about the human body. And there will be lunar gravity, there will be Martian gravity. Right now, our crew have been in microgravity. So what are some of the changes or adaptations that happen to the human body that we need to understand as they stay longer and longer in space, at least in microgravity?
Yeah, so Tara, just as you said, what we see is that the human body actually adapts to microgravity. So this is really interesting. The physiological responses kind of meet the environment that people are put in. So, NASA has developed extensive countermeasures to keep astronauts healthy. So one of the things that we would see without that is you would see muscles atrophy, you would see bone loss. And so our astronauts exercise every day for long periods of time to help mitigate that loss of bone and muscle. Now, they don't necessarily need it as much in microgravity, but that's really supporting their health when they come back to Earth. So that's, like we talked about, those gravity transitions that can be really hard when you have to adapt back to experiencing gravity. We also see astronauts have blood volume changes. So without gravity pulling your fluid in your body down, you get this fluid shift upward. And so people talk about when they first get to space or on the space station that their photos and their pictures, their face will look a little bit puffier. And that's because the fluid in your body starts to rise up. And then your body starts to realize it doesn't need as much fluid. It's not fighting against gravity and having to pump against that to get fluid and blood, in particular, to your brain. So you start to lose the fluid. And then more recently, researchers are starting to take a look at the immune system. This is a really active area of research and see how that changes in an isolated environment. So some of these physiological changes that you see in astronauts, you can also see in model organisms. So with things like mice, these are a good model for physiology and how you can take advantage of that for things like muscle wasting and osteoporosis. And do research in those areas in microgravity.
Thank you, Jennifer. Yeah, the human body is really efficient. So it's use it or lose it is what it is, right? Okay, so the next question is for Marybeth. CubeSats, these cute little CubeSats. We've heard a lot about them, especially over the last few years, tiny little things. What are they? They've been in exciting development. What's a CubeSat and why is it important in science and even in developing the low Earth orbit economy?
So a CubeSat is just that. It's a cube-shaped satellite. It's 10 centimeters by 10 centimeters by 10 centimeters. That's one unit. They call it a 1U. But then you can gang them together and you can make 2Us or 3Us. And now they do 6Us and 9Us. And they just keep making them bigger and bigger. And then you start going, that's not a CubeSat anymore. That's a satellite. But that's a different discussion. So the beauty of them is they've been standardized. They were developed by a professor out in California. And of course, his name is escaping for just a moment, but I'll remember it in a minute. It's the smallest type of satellite, and it allows you a cheaper way to perform science and technology demonstrations in space. The size of it, the 10 by 10 by 10 centimeters, was originally set because that is the smallest trackable object that the Space Command guys could follow, right? And so you wanted to know where the thing was so that you knew if it was going to run into something. Most notably for us, space station, because we really don't want CubeSats to run into us. And anything smaller was not trackable by the ground system. So, but you can do an amazing amount of things with them. Because they've become standardized, there's now standard communication boards that you can just buy from a company and drop in a communication board, or you can drop in a different kind of electronic board to provide you different instrumentation and data, or you can drop in a standard camera if you want to be taking pictures. And so it kind of is like going to the model rocket shop and buying different bits and pieces and putting them in your CubeSat. They've been used for technology demonstrations of different new technologies. They've been used for putting fluidics in, which are really small amounts of fluid and living materials, and testing out how cells and things react and how they grow or not in microgravity. And in the space environment, they've jump-started research in a number of areas. The biggest area they've been used in, though, is satellite companies, using them mostly to be able to quickly mature their technology and their cameras and data systems and optics to be able to get a coverage of the entire globe and get data on how the world is changing with just visual cameras data every day, over time. So companies like Planet and Spire have been kind of grown up out of this CubeSat market. On space station, there have been a number of companies who have deployed CubeSats. There have been now more than 250 deployed from station, initially with NanoRacks and our JAXA colleagues, and now CEOPS and some others have started. But because they're standardized, because they've miniaturized a lot of things, they're pretty cheap. And so that's made them very powerful for learning experiences. There's a lot of senior level design classes in universities, and the students in aerospace, they have to build a CubeSat. And then there was a big problem with there's all these CubeSats on the ground and they couldn't get launched. So NASA started the CubeSat Launch Initiative, and we started taking those in from academia and finding ways to deploy them. A lot of the ones deployed from station were part of the CubeSat Launch Initiative, where we allowed academics who otherwise couldn't afford to launch their CubeSats, because launches are still very expensive, a way to get those student experiments into space. If they're commercial, then we've said, yeah, you got to buy your opportunities. So, but all of this new business was really the first business case that developed from some idea to actually generating revenue, making money for the low Earth orbit economy. It was kind of the unexpected first product or thing that could be sold. And I'll tell you, for some of us, it was completely unexpected. Well, for all of us, it was pretty much unexpected and very eye-opening. And for some of us, it was kind of frustrating, because I used to tell people, look, we didn't build this amazing science platform to open up the back door and throw stuff out. But that's what we were doing, was throwing stuff off the back porch. And but it was important because it was a different kind of science than we envisioned. But it was also, commercial and generating revenue and really revolutionizing an industry. So sometimes you have to get comfortable with using the platform in ways that you really didn't think of, and that when they happen, you just look at it and go, it's such a waste of such a cool platform, and realize it's not a waste. It's just a very different idea than you had when you started, and that's okay.
Thanks, Marybeth. I remember the first time I was hearing about the CubeSat program, and the way they work is you put them on a rocket, you package them up, you put them on a vehicle that launches to station, and then you load them in this launcher, which is like a soft cannon, and poof, they just go out. They go away from station. And I remember thinking, like you said, they want to what? Like shoot something out of the back of space station? Like that's insane. But the really cool thing about working in station is we do these things, like you said, that we wouldn't have thought to do unless you. I mean, it's kind of crazy. We do the crazy things, and it's really useful. It's been useful for science. It's been useful for low Earth orbit economy. So it's a really cool story about the CubeSats. Now I have a question for each of you, a little bit more on the personal level, and I wonder, are there any particular stories about your time working in the space station program that have stood out to you? Either something happening on orbit or in training or on the ground? Let's see, I'll start with Kirt.
Okay. I was thinking about this the other day, and a couple of years ago, one of the benefits of being involved in the science program for ISS is getting to go out and interact with all the professional societies that are out there. And one of them that serves the microgravity field specifically is the American Society of Gravitational and Space Research. So about 4 years ago, I was invited to talk during their scientist career day. And it turned out to be just an absolutely amazing event. We had a ballroom full of high school students and middle school students. And not only did I get to talk about everything cool that was going on board ISS, but I also got to talk about the path that got me from a very small rural high school in Kentucky to being, at the time, the deputy chief scientist for the space station program. I think it was amazing knowing that those kids in that room were there not because they were getting extra credit, but because they actually had an interest in doing science in space. And it really left me feeling, after talking to them and hearing the questions that they asked, that the next generation of space explorers and researchers is out there. So I hope that day they were a little bit inspired by what I said, but they also inspired me. They inspired me with the confidence that this field is here to stay, and we've got a great future ahead of us.
Thank you, Kirt. How about you, Jennifer? Do you have any interesting stories of your time in space station?
I do. So one really interesting experience I got to have in space station was actually participating in an experiment that we did on ISS. So for a little bit of background, my background is science, and when I first came to NASA, I actually worked in the Flight Operations Directorate. It was during the assembly phase, and so we're really focused on constructing space station. And so I worked in flight operations and actually was in the system for life support. So I worked on a lot of the regenerative stuff Marybeth talked about earlier. So after supporting operations for about a decade, I came back to science and started working in the ISS program on the science side. And one of the issues that we were trying to address at the time was how we're changing operations of how we're doing stuff in the open cabin. And so I was looking at it from the biology side on how can we make this more like a ground core lab. And so I worked with some folks to design an experiment to test some of those things. And it was a really amazing experience to kind of be on the other side of it. To see things through the eyes of a scientist and as a payload developer, executing research on space station and to get that experience. Coming in the door, you get access to all of the expertise that NASA has. So even though my background is biology, I was partnered up with two of the folks who are our, space fluid physics experts, which was really great to work with. I learned a lot from them, but definitely something that I never imagined I would be doing. And then, getting to sit over in MCC in one of the smaller flight control rooms and actually talk on space to ground to one of the astronauts doing our experiment was just an amazing experience. And all the things Kirt talked about earlier, right, of, collaborating with them as you're going back and forth on something might not work exactly right, but, they have suggestions. And so you're really kind of partnering also with the astronaut who happened to be a scientist on board to accomplish your research. So that will always stay with me as just an amazing experience of having the opportunity to do that and get to work with those groups of people.
Yeah, that was a fun one, Jennifer. I loved watching that because, like I said, I followed space my whole life, and every scientist knew you couldn't micropipette in space. It wasn't so easy to transfer tiny little drops of fluids from one tube to the next. But when Kate Rubins got up there and you guys decided to tackle it, I mean, you all tried something different, tried something new, and proved that it could be done. And it's like a breakthrough for science now that we can do lots more on station. And that was a really fun time. And you got to be the principal investigator for some of that work. So that was great. How about you, Marybeth?
Yeah, so I've got three little snippets all related to the same person and same sort of events. So when I first came to space station science, it was I had been working on life support systems, like I said, and I came in to help develop this concept of a ISS as a national laboratory and bringing in new users outside of NASA and outside of the partnership. And one of the first people that I ran into in this world was a guy named Jeff Manber. And he had put in a proposal to be able to fly his own commercial facility to space station and to bring in his own customers. And it was built off of the CubeSat concept, but he took that same thing and said, let me put it inside. And he called it a Cube Lab. I thought, well, that's not terribly creative, but okay, that's fine. And in talking with discussions with my counterpart at headquarters, Mark Uran, he thought, no, this will never work. This isn't the kind of thing we want. But in the end, he said, sure, go ahead, sign a Space Act agreement. Let's give him a shot to fail, because Mark was sure that we weren't going to do that. And what Mark didn't know is that's kind of, the red flag in front of the bull for Marybeth. So when he tells me to go ahead and do something so we can see if, just give him a chance to fail, I'm like, oh, no, we're not going to fail now. Now we're going to find a way to make this work. And I really didn't have anything to do with it. Jeff, and at the time, I think he had one or two other people in less than 6 months, went from signing a Space Act agreement to flying their little Cube Lab platform with their first customers, who were education customers, people who had gotten students to build experiments on board. And that was really the beginning of this new kind of world where commercial companies were bringing in their own users. And it was really hard for us to accept that they were going to pick the science and that it may not be the same kind of thing we would do, that it might be much, much different. And our operations teams really struggled with, what is mission success? What does it mean, right? Because it's their payload and it's their thing. And so we really had to spend time talking about what success means and what's his job and what's our job. And in fact, we asked Jeff to please come to Huntsville and talk to the operations team. We brought them all together in a big room, and he flew down. He's based in DC himself, and he flew down and kind of explained, this is what I'm trying to do. This is what my company does. And this is my job. And this is what I need, NASA to do. But this is my job now, this part about mission success. And through the course of the discussion, I don't remember how it came up, but he mentioned he had flown into Birmingham or Nashville on Southwest and driven to Huntsville instead of flying the direct carrier from DC. And somebody said, well, why did you do that? And he said, well, because I have to pay for my plane fare, and it's a lot cheaper to fly Southwest to one of these places than it is to fly direct. And everybody in the room just kind of went, oh my word, this matters, right? That the difference in a cost of a plane ticket matters to this commercial company and how much he's spending. And at the end of the meeting, one of the people who was there, because Jeff had just kind of told his story and explained, how the world works from his point of view as a businessman. One of the women, Pat, said, if he'd have handed out a hat and we'd have done a collection at the end, I'd have given him money, right? Because they were just it was such a different shift in thinking about what this was and how this was going to work in this new world order. And then it was a number of months later, and we were all still learning about, things like, okay, what is the business consideration? What matters to this businessman about this decision we're about to make? We always thought about the business impacts to NASA and the costs to NASA, but we had not gotten in the habit of asking business questions of our partners, of our commercial partners. And I was in Huntsville, and there was something going on orbit that I don't even remember what it was. And they were going to make a decision about some real-time things, and it was regarding a NanoRacks payload. And I remember calling Jeff and saying, hey, look, we've got to do this or this, and this would delay your science, and we need to know, does that impact you? Are you waiting on a payment for when this thing happens, right? I mean, do you get paid when you do this science, or does that not matter? And he said, hang on, let me go check, right? And called me back a little while later, and whatever the answer was. And I fed that answer up the line, and said, well, this is what happens if we slide this one or don't do this one. And in the end, the decision came back. We ended up having to slip that, the answer ended up being no. We were going to slip the NanoRacks work because some of the other science was, couldn't wait. It was, living science, and we'd have lost the science. And so his got pushed. And I called him back and gave him the news, and said, look, I'm sorry, but we're going to have to push your science. And he said, thank you. And I said, what? Thank you. And he said, this is the first time anyone has even asked the question, and it's been considered in decision making. And so it doesn't matter that the answer is no. It matters that you guys are all, as an agency, starting to change your thinking and think not just about the NASA needs and the NASA costs, but the business costs to those of us who are using the platform and the science all at the same time, right? That it was a monumental change and shift in thinking in his mind, that the business considerations for his little bitty company were even discussed. It didn't matter what the answer was at that point. It just mattered that we asked the question. And so, for me, these kinds of things where it was like, okay, that wasn't the answer I expected, but that mattered more than I realized, and started us really thinking about changing our culture to really being responsive to the needs, not just of the people picking the science, but the people who are implementing the science, the payload developers, and the people who are trying to execute the science, the principal investigators. All of them are part of our community, and we have to be able to work with all of them. So it's been a lot of little things that really kind of add up to me to this. This is a different world that we're in than we have ever been in before.
I did not know that story. That is really cool. And look how far we've come. That must have been about 10 years ago, because I remember meeting him as well right away. Yeah,
we signed a Space Act agreement on 9999.
Yeah.
Or 9901. I guess it was 9901, something like that.
Yeah, that's when I joined. I joined in 2009 is when I joined the office. So you might be thinking 09. 09, yeah. Okay, so that's cool. And like you said, like small businesses would have never thought. I mean, it was not all that. It was all NASA using station, all NASA. And now we've started there, and now we have a whole Space Station National Lab component that offers opportunities for researchers to use the station through academia and business and government. And NanoRacks was the first one, right?
10 different companies with 21 different pieces of their own hardware, their own science capabilities on board, and they are out finding customers, which include NASA and include other parts of the government. And that's a way different world than it was a decade ago. Way different than 20 years ago.
And it's going to be 20 years difference as we look forward, too. It's growing. And on that note, I'd like to ask, I'll start with Kirt. I'm going to ask the three of you, but I'll start with Kirt, your final question. What do you hope is the legacy for the space station?
Ooh, good question. So I think from a scientist's perspective, we really understand what the benefits of doing research in space are. we talked about them early on, but they can lead to discoveries. There are questions that we can't ask on Earth because the environment isn't right. You have to do it in space. So I think the legacy of ISS is if we can sustain experimentation in that environment. So if ISS has shown us how to do good science in space, we can continue doing that, whether it's on an extension of ISS or in follow-ons, because our researchers need access to that. And that's our NASA researchers and our commercial research and development folks. They need access to space. So I believe the legacy of ISS will really be in terms of low Earth orbit, opening it up to continue to have it as a resource for all of our researchers.
Excellent. How about you, Jennifer?
Yeah, I think the legacy of ISS will be a proving ground for exploration. So just the volume of science we have been able to do in the past 20 years and what we will accomplish in the next decade is going to inform our decisions as we go forward. That's going to help us prove out the technologies we need to go forward back to the moon and especially onto Mars. And so, I think this proving ground is teaching us not only how to do long duration, long-term operations in space, but also how do we develop the infrastructure and the capabilities and some of the systems we've talked about today. And so I think in the next decade, the work we're going to be doing is going to be so important to set the stage for where we go in the future.
The legacy of exploration. Awesome. And I'll wrap it up with you, Marybeth. What's the legacy of ISS for you?
So this may sound corny, but for me, the legacy of ISS is that we've changed the world, and in sort of three key ways. The international collaboration, whether it was through assembly and all the partnerships, or now with research and all of the research where we are partnering with our research counterparts across the world. It's amazing what we have learned and continue to learn from each other and working together in ways that we never would have done, 40, 50 years ago. The other way, that I think we're changing the world is that we're learning things we never knew we didn't know. And we're going to use those things for the betterment of humanity. We won't know what those things are for, maybe a decade in some cases. We've just started seeing the results and the impact of the research that was done a decade ago and a decade before that, and that will continue to multiply. And in 50 years, we won't realize how much of the changes in the world came from work that was done on space station. And then the third way that I really think that we're changing the world is opening up an economy in low Earth orbit, a place where people can live and work in space. Just like Jeff Bezos and others say, we are using space station as an accelerator, a platform, a springboard to really create an economy in low Earth orbit, so that we can get off of this planet and have options beyond here. And that's going to be the legacy of ISS. It's not going to be recognized for a while, but it's changing the world, whether people see it now or not.
Beautiful. I see it now. You're right. It's beautiful. It's going to live on for generations. And with that, I think that was a good way to wrap up. The fact that we and future generations are looking forward to several more years of exciting discoveries on the station. You, the viewers, can keep an eye out for more informative and fun interviews like these in our ISS 20th Anniversary Celebration Series. Thank you, Marybeth. Thank you, Kirt. Thank you, Jennifer. I miss you all. It's good to see your faces. Good to reminisce with you on station science and technology. Bye for now, everyone.
Bye. Thanks, Tara.
Thanks, Tara.